Bismillahirrahmanirrahim. Welcome to the online course of integral equations. We have started chapter 2 and discussed some methods for solution of predominant integral equation of second kind. In today's lecture, we will discuss about the successive approximation and successive substitution method for the solution of predominant integral equation of second kind. Desired learning outcomes of the current lecture. After this lesson, students will be able to know the general procedure of the successive approximation and successive substitution methods for the solution of predominant integral equation of second kind. Also, students will be able to apply these methods to some test problems. Initially, we consider the predominant integral equation of second kind defined in 1, where in 1 k of xt represent the separable kernel and u is the unknown function to be determined. In this method, we replace the unknown function under the integral sign, which is basically u of t, by any selective real valued function u0 of x, where x lies between a and b. Accordingly, the first approximation u1 of x of the solution u of x is defined in 2. Similarly, the second approximation u2 of x of the solution can be obtained by replacing u0 of x in 2 with the obtained approximation u1. Hence, we find the u2 approximation given in 3. This process can be continued in the same manner to obtain the nth approximation. In other words, the various approximation of the solution u of x of equation 3 can be obtained in the following recursive scheme, where in the recursive scheme, first we select u0 of x, which is any real valued function, and then we calculate un of x is equal to f of x plus lambda integral from a to b k of xt un minus 1 of t dt for n greater than or equals to 1. Remember, for n equal to 1 we are getting the first approximation, for n equal to 2 we are getting the second approximation, and so on. Here we discuss some key points of the current method. Initially, we can select any real valued function for the zeroth or initial approximation u0 of x, but for simplicity we take u0 of x 0, 1 or x. Second, at the limit, the solution u of x will be equals to limit n tends to infinity un of x, so that the resultant solution is independent of the choice of u0 of x, which means that different choices of u0 leads to the same solution. Third one is, it is important to distinguish between the recursive scheme used in the Adamian decomposition method and in successive approximation method. In Adamian decomposition method, we apply the approach to determine several components of the solution, and then we add finally all the components. So the zeroth approximation or the zeroth component of the solution u0 of x in the ADM techniques defined by all the terms that are out of the integral sign are part of these terms if the modified version is used. However, in successive approximation method, we apply the recursive scheme to determine various approximation of the solution itself and not components of the solution. Now we take a specific example to test the successive approximation method. We consider the predominant integral equation of second kind defined in 4, where in equation 4, kernel k of xt is equal to xt, which is separable. Initially, we take the zeroth approximation u0 of x is equal to 0. Now by plugging this u0 of x equal to 0 in equation 4 instead of u of t, because t and t is the dummy variable, so the integral part will be equals to 0, and consequently u of x will be equal to x, and this u of x is our initial approximation, which we relabel u1 of x is equal to x. Proceeding in the same manner, we find that u2 of x will be equal to x plus lambda integral from 0 to 1 xt, and now instead of u of t or u0 of t, we replace this with u1. So u1 of x is equal to x. Here we have used dummy variable, so u1 of t will be equals to t. So t multiply t, that should be t square. Now taking x out of the integral sign and integrating t square from 0 to 1, we are getting just t cube by 3, and from 0 to 1, so that should be just 1 by 3. Thus u2 of x is equal to x plus lambda times x by 3. Continuing in the same manner, we obtained u3 of x is equal to x plus lambda integral from 0 to 1 xt and to 1 plus lambda by 3 t dt. You saw in previous slide that u2 of x was equals to x into 1 plus lambda by 3. Here we have used u2 of t, so that's why we have replaced u2 of t by 1 plus lambda by 3 into t. Now by taking x into 1 plus lambda by 3 out of the integral sign and integrating rest of the expression, we get u3 of x is equal to x plus lambda by 3x plus lambda square by 9x. Generally, we obtained for the nth approximation un of x is equals to x plus lambda by 3x plus lambda square by 9x plus and so on lambda power n minus 1 by 3 power n minus 1 x, where n greater than or equals to 1. In equation 5, by plugging n is equal to 1, we are getting the first approximation, then n equals to 2, we are getting second approximation, and so on. Consequently, the solution u of x will be equals to limit n tends to infinity un of x. So by plugging the value of un of x, we have equation 6. Now you can see x is common in equation 6, so by taking x common, we have a geometric series of the form 1 plus lambda by 3 plus lambda square by 9 plus and so on. The first term of this geometric series is 1, and the common ratio, this is equal to lambda by 3. So this is infinite geometric series, and this sum will be equal to a 1 by 1 minus r, where r is the common ratio. Here the common ratio is lambda by 3. So by taking this the summation of this geometric series, we obtained that un of x will be equal to 3 by 3 minus lambda x, and this is the final solution by using the successive approximation method. We discussed earlier that u of x obtained in equation 6 does not depend on the selection of u0 of x. To clarify this, again we solve equation 4 by selecting u0 of x is equal to x. Using the new selection of u0 of x in the right hand side of equation 4, the first approximation u1 of x is equal to x plus integral from 0 to 1 xt u0 of t dt. Since u0 of t is equal to t, that's why u1 of x is equal to x plus integral from 0 to 1 xt square dt. By evaluating this integral, we get x plus lambda by 3x. Similarly, u2 of x will be equal to x plus lambda integral from 0 to 1 xt into u1 of t dt. Since we computed u1 of x is equal to x plus lambda by 3x, so we substitute u1 of t is equal to t plus lambda by 3t, which gives u2 of x is equal to x plus lambda by 3x plus lambda square by 9. And continuing in the same way, the nth approximation un of x is given in 7. Accordingly, we obtained u of x is equal to 3 by 3 minus lambda x, which is consistent with the same result obtained above in equation 6. Thus, u of x is independent of the choice of u naught of x. Here we start another method, the method of successive substitution for the solution of freedom integral equation of second kind. This method introduces the solution of the integral equation in a series form through evaluating single integrals and multiple integrals as well. The computational work needed in this method is huge compared with the other techniques. To discuss the basic theme, again we consider the freedom integral equation defined in 9, where k of xt is again the separable kernel and u is the unknown to be determined. Initially, we set x equal to t and t equal to t1 in the freedom integral equation defined in 9 to obtain 10. Now, we substitute equation 10 in equation 9, or we just replace the value of u of t from equation 10 in equation 9, we get equation 11. So in equation 11 you can see that we have single integral as well as double integral. Also this equation 11 can be written as f of x plus lambda integral from a to b k of xt f of t dt plus lambda square integral from a to b integral from a to b k of xt k of t t1 u of t1 dt1 dt. You saw in previous slide that we have u of t1 term in the last integral. To calculate that, putting x equal to t1 and t equals to t2 in equation 9, we obtained equation 12. Using the value of u of t1 obtained in equation 12 and to the right hand side of equation 11 leads to equation 13, and so on. Accordingly, the general series form for u of x is given in equation 14. Equation 14 can be obtained by plugging u of t2 in equation 13 as we substituted u of t1 in equation 11. Here we consider a specific example to test the successive substitution method. For this we consider equation 15. Comparing equation 15 with equation 9, the value of lambda is equal to 1 by 8, f of x is equal to 23 by 6x, and k of xt is equal to xt. Using these values in equation 14, we get equation 16. In equation 14, the first term was f of x, which has been replaced with 23 by 6x. The second term in equation 14 was lambda integral from a to b k of xt f of t dt. So lambda has been replaced with 1 by 8, integral from a to b with integral from 0 to 1, k of xt with xt, and f of t with 23 by 6t. So the resultant integrals become 1 by 8 integral from 0 to 1 23 by 6xt square dt, plus the third term in equation 14 was lambda square integral from a to b integral from a to b k of xt k of t1t and f of t1 dt1 dt. So lambda square has been replaced with 1 by 8 square, double integral has been replaced with 0 to 1 0 to 1, k of xt with xt, k of t1 with t1, and f of t1 with 23 by 6 t1. So the resultant integrals become 1 by 8 square integral from 0 to 1 integral from 0 to 1 23 by 6 xt1 square t square dt1 dt, and so on. Now evaluating the integrals in equation 16 and taking 23 by 6x common, we have equation 17. So the first integral in 16 is 1 by 8 integral from 0 to 1 23 by 6x t square. Taking 23 by 6x out of the integral sign and integrating t square from 0 to 1, we are getting 23 by 6 into 1 by 24. So by taking 23 by 6 common, we are getting just 1 by 24. And similarly evaluate the double integral, we are getting 1 by 576 and so on. Now in equation 17 you can see that there is a geometric series which is 1 plus 1 by 24 plus 1 by 576 and so on. So the first term is a1 and the common ratio is 1 by 24. By using the formula that the geometric series sum will be equal to the first term divided by 1 minus the common ratio. So by simplifying this we are getting 23 by 6x into 24 by 23. So 23 cancel and 624 will be equal to 4 and x will be equal to x. So the solution becomes u of x is equal to 4x.